Hello, my name is Sasha Stevens, and I'll be presenting on the structural engineering focus sequences available at UCSD. Let's hope I can get through all this in 4.5 minutes. All right, what is civil engineering? Civil engineering refers to civilian engineering. So that would be structures based on transportation, shelter, and other civilian needs. So there's a few different subcategories of civil, mainly civil structures, earthquake, hydraulic, environmental, and transportation. Now there are more, but these are the main ones. So civil structures. Civil structures refers to things like bridges, offshore buildings, and tunnels. Now, transportation is an interesting one because it has a structural side, such as an airport or like the light rail at UCSD or the infrastructure at a bus stop. And it also has a non-structural side. This is like a transportation map of a subway. So, and also another good example would be air traffic control at an airport, but those are non-structural engineering needs to happen for the structure to run. Hydraulic engineering. Now, hydraulic engineering deals with a lot of water. So over here we have an example of a dam, which is structural hydraulic engineering, and this is a canal, also structural. But then over here we have a heat map of different aquifers, and that would be related to more non-structural hydraulic engineering. We also have environmental engineering, which has a structural and a non-structural side. The structural side of environmental engineering would look like the windmills that produce electricity, those structures, or the structures behind a waste treatment plant. But then the actual chemistry that goes on inside that plant, that would not be considered structural environmental engineering. Earthquake engineering. So earthquake engineering does have a structural and a non-structural side as well. Structural side would look like repairing and assessing risk of buildings, versus the non-structural side would be creating maps of where likely earthquakes are going to happen and creating regulations around that. So what is geotechnical engineering? Geotechnical engineering is, in a word, soil engineering. See, all these examples right here deal with earth and soil. So soil isn't just dirt. I was quite surprised myself. So soil is made up of dirt, particles like rocks, and liquids like water, and gases like air. And all this makes a very, very complex composite known as soil. So what geotechnical engineers do to survey the soil is they take this like pipe and they stick it down in the ground in an area that they want to survey, and they bring it out and split it in half, and then they can check and see the different compositions of the soil as it goes up through the earth. Now, what is going on with that crazy soil? From that sample that geotechnical engineers take, they can determine the shear strength of the soil, the compression, the heat characteristics, and the permeability. Now, all this matters because was this crack always there? Probably not. All these factors over time can make your buildings crack, which is why we need geotechnical engineers to help us make sure this doesn't happen. So soil is built different. Soil is a very, very interesting phenomenon that when used wisely will help structures, but when not, will, right here cause dam failure, and over here invade our transportation, which is a good example of how all these versions of engineering are intertwined with one another. Like on these job sites, you definitely don't just have geotechnical engineers cleaning up this mess. There's also transportation engineers, structural and non-structural, and plenty of other engineers working right here. What is structural aerospace engineering? So right here, a good example is to show the different types of aerospace engineering over the years. Right here, we have a very modern example, which uses fancy composites like carbon fiber, and is an example of very stiff structure. And over here, we have an early version of a plane, which is made out of a very basic and primitive material like wood and is not stiff. Now, an interesting thing about aerospace structures is that you don't just have to go into aerospace with it. Because it's dealing with composites and interesting complex structures, it's more versatile and can be used in aerospace, of course, as well as satellites, cars, naval, and sports equipment. So who does aerospace? That's a good question. The actual aerospace part can be done by plenty of different companies like Raytheon, Boeing, Northrop Grumman, NASA, the Air Force, in San Diego, we have Collins Aerospace, which is a subsidiary of Raytheon, and plenty of aerospace companies being contracted and subcontracted out there. So easy to find them. What are the flappy doos called again? No, I'm referring to the aileron, rudder, and elevator, which control pitch, roll, and yaw. Aerospace is pretty cool. I do like aerospace structural engineering, and it is the route I tend to go on. I find it to be so interesting because you can really take your degree anywhere. You can take it to go build, rockets for SpaceX, or you can take it to a niche market like rock climbing gear. That kind of versatility is something I really value in my degree. And yeah. All right, SMH isn't simple harmonic motion. I know I was confused too. It's actually structural health monitoring. Now, structural health monitoring is comprised of two main sequences. First, the damage detection phase, which right here is building looks pretty damaged, and then the need-based. So right here, then we evaluate the damage and we see if we need to repair it, demolish it, or if the structure is safe at all. All right, now how to inspect. Now there's just two real main schools. We can have the sensors or the manual visible inspection. So right here, it's very costly to do manual visual inspections, and it takes a lot of time. Whereas if we can embed sensors into our systems, then we don't have to have such a costly effort. That's also very time consuming. It's very instantaneous and quick. Although any foresight overlooked by our sensors will not be known. And there are two flavors of sensors. We do have wired and wireless. Of course, wireless being the fancier of the two. All right, with testing. So once a structure goes up, structure like a bridge, you might want to test to see if the load capabilities of the bridge are what you thought they were. So say you send a heavy truck across the bridge and you may monitor it at different points along the bridge. That can be used in simulations and hand calcs to determine if the bridge is performing as expected. Over here, we have a weather device that's measuring how the bridge performs in weather, again, to see if it's as expected. NDI and NDE. This refers to excitation, sensing, and detection phases in structural health monitoring. All right, and that's all, folks. Thank you for coming to my presentation. I know it was a little bit longer than 4.5 minutes, but it's a lot of content to cover in that time.